Well, again, continuing with Unit 1, we are going to move on to Section 4.4 today. We're going to do more factoring. This time we're going to be factoring quadratics when A is some other number other than 1. So after today, your goal, you should be able to completely factor quadratic expressions of the form ax squared plus bx plus c. It's really going to be the same process we did yesterday. The only difference is A is not going to be 1 every time. So, factoring 2x squared plus 9x plus 7, I have a little hint up here. When C is a positive number, then both factors have to have the same sign. So C is the last term, notice it's a positive 7. Since the sign in front of 9x is a positive as well, that's going to tell us that both factors will have to be positive. So just keep that in mind. It's something to think about as you're going through. It's going to help you to keep your possible combinations more organized and more succinct instead of using extra combinations you don't need. Anyways, we're still going to do bottoms up. First thing you want to do, though, is check to see if there's a monomial term that you can divide out of both or all 3 terms. In other words, look at 2, 9, and 7. Is there a number that will divide 2, 9, and 7 other than 1? Well, 2 is a prime number and 7 is a prime number, so that tells us there is no other common factor other than 1 for those numbers. We also look at the variables, the x. If x is in all 3 terms, then we can factor out some power of x. X is only in 2 out of the 3, so we cannot factor out an x. Some people like to try and pull an x out and make it x times 2x plus 9 plus 7. That doesn't really help us in terms of factoring the entire trinomial. It's a good thought, but it won't really help us in factoring. So once you always start out when you're factoring, I mentioned this in the previous lesson, but always start out by looking for some monomial term that you can pull out or divide out, so to speak. This one doesn't have it, so we're going to start with bottoms up. Bottoms up, remember, we make a table. In the table, we do what multiplies to make A times C. In this case, that's 2 times 7, or 14. And what adds to make B. In this case, B is 9. So I'll give you a second here. Think about what combinations will multiply to make 7, and then also multiply or add to make 9. Some of you may see it right away, but you can always start with thinking, okay, 1 times 14. That's a combination of multiplies that make 14, but when I add them together, they make 15. So this is not an answer. That's not a combination that's going to work because it has to make 9. It has to add to make 9. So we look, the only other combination that multiplies to make 14 is the one we have up here, the A times C, which 2 times 7 is 14, and 2 plus 7 equals 9. That's our winner. That's the combination that's going to work. So how do we use that? Because we don't just write this as our answer. Remember, we want this to be in factored form. So we know we're going to have 2 binomials. Seems how there was no monomial term to pull out. It's 2 binomials. Our variable is x. So we know there's an x in front of each term as the first term. And since there's 2 plus signs in the problem, as we said earlier, we know it's going to be plus plus. So it doesn't matter whether we put 2 here or 7 here, or we flip these around. That's how we're going to start. Now, is that our answer? Some people would say, yes, that's our answer. But if you FOIL this out right now, we have to get a 2x squared. X times x is not 2x squared. X times x is x squared. So we're missing something. We're missing something. Remember, this method we use is called bottoms up. And we really haven't had to use that yet. But the bottoms up part, if you recall from yesterday, we say, what is A? We have to use that A term in this step. A equals 2. 2 is in front of the x squared, so A is 2. So we're going to put 2 in for A. And what did we do with that 2? What did we do with that A value? Well, if you remember yesterday, what we did is we divide each of the factors, in this case 2 and 7, by that value. Yesterday it was always 1, so it didn't change it. It stayed the same. That's what made it a little bit easier when A is 1. When A is 1, the factoring is a lot more straightforward. So here's this added wrinkle, the bottoms up. And how does this work? Well, we look at each of these ratios individually. 2 divided by 2. Can we reduce that? course we can. What is 2 divided by 2? 2 divided by 2 is 1. So this is going to reduce to x plus 1. Because the 2's cancel out. It's not x plus 0. 2 divided by 2 is not 0. 2 divided by 2 is 1. Check it in your calculator. You don't even need a graphing calculator for that one. Over here, 7 over 2, can that be reduced? Many of you say, no, it can't, of course, but what if you're not sure? What do? Well, on your graphing calculator, there's a couple ways we can check that. If you get 7 divided by 2 and hit math, enter, or math fraction, it'll reduce it for you. And we get the same thing we started with. Let's put this on the larger screen for you to see. We get the same thing that we started with, 7 over 2. That tells me this is already reduced. So if this is already reduced, then what we do is we do the bottoms up part. And what we do is if once you reduce this fraction, the bottom part comes up in front of this x term, whatever our variable is. And we get 2x plus 7. And we now just successfully factored this trinomial into 2 binomials. So that's why yesterday I was really harping on, divide by a in that second step, even though a was 1, just to get you in the habit of it. So now today we're doing it, and you see why we're doing it. Of course, don't take my word for it. You want to check it somehow. The algebraic way to check it is, of course, everybody's favorite, either FOIL or the box method. We'll do the box this time. Remember, you take and put your polynomials on the outside of the box, put lines dividing each term, and then we fill in the box by multiplying. 2x times 1x is 2x squared. That's a good sign. 2x times 1 is 2x. 7 times x is 7x. 7 times 1 is 7. When we line up our like terms and add them together, remember after this you're adding terms. You're not multiplying. You only multiply once. 2x squared plus 9x plus 7. Is that what we started with? Let's check. It is what we started with. It checks, so we can circle this so that we know that's our answer. Okay? So that's algebraically checking it. We get back to what we started with. We FOIL it back out, or we use the box method. We can do it also on our graphing calculator. If you remember yesterday, I told you when you factor these, or FOIL either way, depending on what type of problem you do, you take the starting problem, plug it in y1, and you take what you think is the answer and plug it in y2. If you get the same graph, you're in business. So let's go to y equals. Hopefully everybody wrote down the problem, or both the answer and the problem. If not, you can always pause it and go back and get that. 2x squared plus 9x plus 7 in y1, and in y2 we're going to put what we think our answer is, 2x plus 7 times x plus 1. And when we do this, one way we're going to check it graphically, so let's graph it and see what happens. Here's 1u. It's a pretty good sign. I'm only seeing 1u. My table defaulted back to this odd change in table or interval. So I'm going to go back to my table start, put it at 0, but I'm going to change this back to 1. Remember, you do that by hitting second window. You can make your interval whatever you want, just changing table to interval. If you want to go by decimals, like you want to go by 0.1 for your intervals on the table, you can do that. I'm just going to go by ones because that's going to work for us here. When I look at my table, the cool thing that we see with the table is all the y values are the same. So this is our first equation, the problem we started with, y1. y2 is the equation that we ended up with. And we can see that they both have the same outputs. That's a good sign. That tells us that what we factored is equivalent to what we started with. Now, you may not have factored completely, but you're at least on the right track, and you should at least get partial credit for that. But just another way to check other than foiling or multiplying it out every time. If you have a multiple choice test, for instance, and you don't want to take the time to FOIL it out and you get really comfortable with your graphing calculator, that's a quick way to do it. Okay, but the graph should look the same, the output should be the same, and when we FOIL it, we should get what we started with. So it's kind of a triple check there for you. you check it, especially on a test or a project or you know, ACT. You want to make sure you're getting these questions right, so you know it doesn't hurt to check it multiple times. Okay, so let's move on to another problem here. We have 3x squared minus x minus 2. I'm going to give you guys a second. I want you to think about how you're going to start it. Pause it for right now, and then when you're done, you think you have your answer, restart the problem, and we'll go through it together. You can check your work. Okay, hopefully you attempted this one. If you got stuck, that's okay. We got one more to practice after this anyway, so you know, we're going to practice more in class tomorrow as well. Remember, you make your table, you do the bottoms-up method. So we do A times C, in this case is 3 times negative 2, which is a negative 6. What adds to make B? B is negative 1. Notice also in our problem we have 2 negative signs, and C is a negative. So if C is negative, that means one term is positive, one term is negative. Also, another addition to that, we have a negative middle term. That means that the negative value that we come up with has to be bigger when you take the absolute value of it than the positive value. If the middle term x is positive 1, then that would reverse. Okay, but we're going to look at combinations where one is positive, one is negative, because if C is a negative number, that's the only way you can get a product to be negative. One is positive, one is negative. So we make our table. You came up with different combinations probably. Hopefully you saw that negative 3 and positive 2 multiply to make negative 6, and negative 3 plus 2 equals negative 1. Now, probably on your table you had other combinations, maybe 2 and negative, or 3 and negative 2, maybe you had 1 and negative 6, 6 and negative 1, but I'm just cutting the chase because we're checking it. Okay, but if you systematically go through all the combinations, you will eventually find one that works if it can be factored. So this is correct. This is what we want. What does that mean? Well, our variable is x. It's a minus 3, so x minus 3, positive 2, x plus 2. Is that factored? No, it's not. If you said that was your answer, you didn't quite make it because, remember, we have to get 3x squared. X times x is x squared, not 3x squared. So we have to somehow get a 3x squared out of this, and this is where bottoms up comes in. We are going to divide by a, which in this case is 3. So we're going to divide by 3, so both the negative 3 and the positive 2. 3 divided by 3 is 1, so I get x minus 1. 2 divided by 3, that does not reduce, does it? If you put it in your Quadratics calculator, 2/3 is already reduced, so this is where the bottom comes up, and I get 3x plus 2. And that is how we factor this trinomial. So you pick a method to check. I don't know which one you did. I'm going to FOIL it out because we didn't FOIL last time. We did the box method. You could graph these as well. You know how to do that. If you want to go back, you should get the same values when you graph them. So rewind and go back to the previous problem if you need to refresh on that. I'm just really quickly going to FOIL this just to show that you need to check it at least one way when you're doing these problems to make sure you get it right. We get 3x squared when we do the first. We get 2x when we do the outer. We get negative 3x when we do the inner. And we get negative 2 when we do the last terms. We combine these like terms. We get 3x squared minus an x minus 2. Minus 2. So, is that what we wanted? So I was checking 3x squared minus x minus 2. If that checks, that tells me that my answer up here is good to go. So let's try one more. Same thing here. I want you guys to pause this. I want you to try this one on your own. When you think you got it and want to check your answer, hit play, and we will go through it together. Okay, so I hope you all really try to factor this one on your own, because factoring you need to practice. So you need to try it and know that it doesn't matter if you get it wrong. As long as you're trying it, you're going to get better. So A times C, that's negative 60. 3 times negative 20. Add up to make B. B is 7. Lots of combinations multiply to make negative 60. You probably may have a long list of factors. Hopefully you figured out that 12 and negative 5 multiply to make negative 60. And they also add to make negative 5. Negative 7. They add to make negative 7. So there's our winner. That's our winning combination. Now, obviously, if I was doing this the first time, I probably would have more combinations, 1 and 62 and 30, you know, on and on until we get down to the 12 and negative 5. But as long as you're writing them down systematically, you should be able to start eliminating pairs. I knew one had to be positive, one had to be negative because C is negative. A negative 20 indicates one positive term, one negative term. So just things you should be looking for as your factor if you're going through the process. And believe me, you're going to get better at this. You probably don't believe me right now, but you will. So I have x plus 12 and x minus 5. You could do x minus 5 and then x plus 12. It doesn't really matter. Okay, are we done? No, we're not done. We all know we have to divide by a. A in this case is 3. So we divide by 3 to each of these terms. X plus 12 over 3. 12 over 3 is 4. 5 divided by 3. Well, when we put that in our calculator, refresher on that, we do 5 divided by 3, and we hit math fraction. We get 5/3 again. So this is already reduced. This means the bottom comes up. And we end up with 3x minus 5. We factored the trinomial. Okay? So go through and you want to check that as well. Formulating it. Box, whatever method you use. We'll do the box this time. X plus 4, 3x minus 5. I know it seems annoying to check every one, but you want to get everyone right. You want to master this. Don't be like I was when I was in high school, and I just said, oh yeah, I must be right, and hurried through this stuff and didn't check it. And I knew what I was doing, but I'd always get a couple wrong on my quizzes and my tests because I went too fast. So make sure you're slowing down and you're checking your work. So 3x squared plus 7x minus 20. That's what we started with. And that's what we want. We checked it, so we can conclude that's the answer. You can also check by graphing it as well, looking at the x, y, the inputs and the outputs, the table. You know, use some method to check it. Okay, whatever works for you. Okay, special patterns. Real quick at this because it's really the same idea as what we have done in the past. The special patterns, if we look at this, 16, let's look at the first one, 16n squared minus 36. We have two terms being subtracted. Well, when two terms are being subtracted, we should be thinking either divide by a monomial or difference of squares. Sometimes we can do both. We haven't been able to divide by a monomial, but if I look at 16 and 36, there's some numbers that divide 16 and 36. What's the biggest number that divides 16 and 36? Well, I know 2 will divide them both, but 4 will also divide 16 and 36. So how I rewrite that when I'm factoring, 16 divided by 4 is 4n squared, 36 divided by 4 is 9. So I can get rid of that monomial term. I can pull it out, so to speak. You see how that 4 came out? All I did was I divided everything by 4. Okay. At this point, I have 4n squared minus 9. 9 and 4 do not have any common factors other than 1, so now I have to look for something else. When we had two terms, like this being subtracted, we would think difference of squares pattern. And in fact, this is a difference of squares pattern. 4 is a perfect square, n is a perfect square. So what multiplies to make 4? Not 4, but 2. N times n is n squared, so 2n times 2n makes 4n squared. 9, 3 times 3 makes 9. So I can factor this into 4n times 2n plus 3 and 2n minus 3. You think to yourself, couldn't I have done the difference of squares right off the bat? 16 is a perfect square and 36 is a perfect square. Yep, but then you would have had monomials to factor out of there. So I do the factor the monomials first to make it easier at the end. But you could have done it difference of squares first and then factored. You would have factored a 2 out of each of those, not an n. Where n come from? Talking and writing at the same time. 4 should be 4 there. So you could have would have factored a 2 out of each of those, and you still end up with a 4 total at the end. Okay. Another one we can look at here is perfect square trinomials. Perfect square trinomials. That's if we have a trinomial. We're looking to say, can the first and last terms are they perfect squares? In this case, it looks like they might be. First, I also want to look and see, can I divide out by anything? 9 does not have a common factor with 49. It's sometimes 7, so in 42, you might have common factors there, but all 3 have to have common factors. So let's just look and see if this is a perfect square trinomial. If I look, 3x times 3x, that makes 9x squared. 7 times 7, that makes 49. So if I'm thinking about this, and you might default when you see a trinomial to your, excuse me, bottoms up method, a times c, what adds to make b, you'd really be looking at the same thing. Okay? A times c, what adds to make b. But the number is going to get really big. So that's when I see these big numbers, I might skip this because it's going to be a big combination. Say, maybe this is just a straightforward sum of squares. Or perfect square trinomial, excuse me, not sum of squares, perfect square trinomial. So 3x plus 7, since they're both plus signs, that would make it 3x plus 7 again. And I'm just going to test this and see if it works. If it works, then I have an answer. If it doesn't, then I go back to the a times c, what adds to make b. I'm just looking for these patterns sometimes can make our lives a little easier. So let's FOIL it this time. Try and alternate between methods. We get 9x squared. We get 21x. We get 21x. We get 49. We add these up. We get 9x squared plus 42x plus 49. So that's what we started with. So this is our answer, except for perfect square trinomials, if it's repeated, we can rewrite it as 3x plus 7 in parentheses squared. So this would be the proper way to write it. Okay? I might point that out on a paper if you turn it in this way, that I prefer it to be written as one binomial being squared. Okay? So that's pretty much the new stuff for today. Hopefully you feel pretty confident in being able to factor quadratic expressions with the form ax squared plus bx plus c, when a is something other than 1. And tomorrow we'll get more practice with this in class. We'll bring you notes, including the goal or the goal of the lesson, or the I can statement, in this case the I will statement, and you'll see it tomorrow in class.